Hi Bobcats! In this lecture we're going to take a look at some ways that we can convert between moles, which we recently introduced, and the representative particles for that particular substance, and atoms, even if the atoms are not the representative particle, grams and liters. We'll be taking a look at this diagram over on the right a little bit more. I'm going to refer to this as the mole triangle, and you'll see shortly how we're going to use this one. All right, so to get us in the right frame of mind for doing this, I wanted to do a quick review of dimensional analysis. We've already taken a look at how we can take something like the formula for ibuprofen, and this formula is telling us that if we have one molecule of ibuprofen, and remember that there is no standard abbreviation for molecule, so I just use a capital MC because that doesn't conflict with any other abbreviations that we commonly use in chemistry. So for every one molecule of ibuprofen, the subscripts in this formula are telling us that we have 13 atoms of carbon, and we also have 18 atoms of hydrogen, and we also have 2 atoms of oxygen. Now, I am not trying to tell you that 2 atoms of oxygen are the same thing as 18 atoms of hydrogen or 1 molecule of ibuprofen, but what I'm saying with this list of equivalents is that if you have 1 molecule of ibuprofen, you also have 13 atoms of carbon, or 18 atoms of hydrogen, or 2 atoms of oxygen. So we can use those as equivalents in dimensional analysis. So this question here wants us to figure out how many atoms of hydrogen are in a sample of ibuprofen that has 26 atoms of carbon. All right, so dimensional analysis. We're going to take the number, the unit, and the chemical that we're given to convert and stick that over 1. So 26 atoms of carbon, and we're going to place that all over 1. Now, if you are really comfortable multiplying whole numbers times fractions, there's no need to put this over 1. I've just found over time that students are generally more comfortable with a fraction times a fraction, so I just stick it over 1 because that doesn't change the value any when we divide by 1. And then the next thing that we need to do is multiply our given by a conversion factor. And when we set up the conversion factor, we want to make sure that the units we have in the given are going to cancel out. So I'm just going to go ahead and write in atoms of carbon. And then in the top, we're going to put the thing it is that we're looking for. In this problem, we're looking for atoms of hydrogen because the problem says how many atoms of hydrogen. So I'm going to just put atoms of H on the top. And now I'm going to look at all of those equivalents we just wrote out. And it looks like with carbon, we've got 13 atoms. And with hydrogen, we have 18 atoms. So I'll just stick those numbers in there. And then I'm just going to run that through my calculator. And remember, for these problems on your calculator, you start with any number that's on the top. So I tend to just go left to right so I don't forget anything. So I'm typing in 26. And then any other number that's on the top, we're going to multiply by. So times 18. And any number in the bottom, we hit divide by. And so divide by 13 and then enter. And that's going to give me 36. This sample has 36 atoms of H. Now, I probably didn't really need my calculator to do this. Let's just point out a couple of things. Atoms of carbon are going to cancel with atoms of carbon. And then the other thing, notice I've got a 13 in the bottom and also a 26. Both of those can be divided by 13, so that becomes a 1. And 26 divided by 13 becomes a 2. So then I've got 2 times 18 is equal to 36. All right, let's try the next one. I just wanted to put into words our dimensional analysis procedure. We're going to put our number, unit, and chemical over 1. That's what we're given. Right, so this first fraction represents what we're given. The second fraction is our equivalents, written in two things we know are equivalent, written as a conversion factor. when we set this up, I tend to build these from the bottom up. Down in the bottom, I'm going to match what I already have been given, and up in the top, I'm going to put what we're looking for. And you'll notice atoms of carbon are going to nicely cancel out, and then, whoops, I kind of wrote over some of that. We can also cancel out a 13. It often helps if you can do any simple cancellations that you might happen to notice. All right, so our new thing here is going to be doing mole conversions. We introduced the mole and said that 1 mole was equivalent to 6.02 times 10 to the 23rd representative particles. And remember that representative particles depend on what kind of a substance you have. If you have an ionic substance, we're going to call those formula units. If you have a covalently bonded substance, we're going to call those molecules. If you have most of the elements, we're going to call the representative particle an atom. If you have one of those Brinkelhoff elements like oxygen, where we have to put a subscript of 2 on them, then the representative particle becomes a molecule. And if we're talking about something like sulfate ions or chloride ions, then the ion would be your representative particle. Let's see, we also have in this chart molar mass. Molar mass is where you're going to take the subscript on any element in the formula and you multiply it by the average atomic mass from the periodic table. All right, so that's something we're going to get from the periodic table, and then you add that up for all of the elements in the compound. This is one thing that's easier to do than to describe how to do. And then last but not least, we're throwing something new in here, which is 22.4 liters for a gas at STP. So STP stands for, I'll write this over here to the left. It stands for standard temperature and pressure. And the numbers that go with that are 1 atmosphere for the pressure, and for the temperature, 0 degrees C. So if you have a gas at 0 degrees C and 1 atmosphere of pressure, and you have 1 mole of that gas, it's going to have a volume of 22.4 liters. Okay, so these 4 things are all different ways of describing the same sample of a gas. If you've got 1 mole of it, you've got 6.02 times 10 to the 23rd representative particles. It weighs an amount equal to its molar mass in grams. And if the substance is a gas at STP, it has a volume of 22.4 liters. And so we can easily convert with dimensional analysis among any of these 4 quantities. Following the procedure of dimensional analysis, we're just gonna pull 2 numbers off of this density triangle, or I'm sorry, this isn't the density triangle. I actually do not like the density triangles we've talked about before. This mole triangle, we can pull any 2 numbers off of this mole triangle and build that second fraction in dimensional analysis, that conversion factor. Okay, instead of talking about how to do it, let's just do it. This problem wants to know how many moles are in 3.54 times 10 to the 24th formula units of sodium chloride. Okay, first thing we need to check, if we have the compound sodium chloride, is the formula unit going to be the representative particle? Well, formula units are the representative particle for ionic compounds. Sodium chloride is a metal plus a nonmetal, and that makes it ionic. So yes, this is asking us to find representative particles of this compound. So I'm going to start with the number, the unit, and the chemical that we were given. So I'm going to start with 3.54 times 10 to the 24th formula units of sodium chloride. And I'm going to stick that all over 1. And then we're going to multiply it by two things off that mole triangle. And I rewrote all of this stuff on that mole triangle down here at the bottom. What we want to do is match units. Formula units are hidden down here with representative particles. Formula units are the representative particle for ionic compounds. So that's going to match things on the bottom. We're going to match formula units of salt with 6.02 times 10 to the 23rd. And up in the top, we're going to put what we're looking for. Well, we're asked to find how many moles. So the thing that has moles with it is the number 1. So up there in the top, we're going to put 1 mole of sodium chloride. And so out of those 4 things on the mole triangle, Avogadro's number of representative particles goes in the bottom, and 1 mole is going to go in the top. Now, if I run that through my calculator, remember we're going to use the EE key for scientific notation. So I'm going to have 3.54 EE 24 times 1. Actually, didn't have to type in the times 1 because that doesn't change things any. And then divided by 6.02 EE 23. Enter. And that gives me an answer. Let's see, I marked this up so much. I'm going to write the answer up here on the top. My calculator is saying 5.880398671 times 10 to the 0. Okay, any number raised to the 0 power is 1. So that times 10 to the 0 is just saying times 1, so I don't really need to write that and multiply by it. And then I also need to consider significant figures. For significant figures in scientific notation, we look at the numbers that are in front of the power of 10. So the number we were given, 3.54 times 10 to the 24th, has 3 sig figs. 6.02 times 10 to the 23rd, that only has 3 sig figs as well. And when we're multiplying and dividing, we round to the smallest number of sig figs. So if I'm going to round to 3 sig figs, I'm going to end up here with 5.88. Now, in terms of units, formula units of salt cancel with formula units of salt, leaving just moles of NaCl. All right, let's take a look at the next one.